So previously, we described Gauss's law in integral and differential form. We're going to wrap up by introducing a theorem that ties the two together. And so this theorem is called the Divergence Theorem. And sounds fancy, but it's something that, if you think about it, you know already, at least in the case of this electric field analogy, in the situation of electric fields. Now, first of all, this is a theorem that is very general. It works for all vector fields. But if you look specifically in the case of electric flux density, or D, you can kind of intuitively explain this using words. I'm going to write out the divergence theorem as stated here, using the capital letter D as our vector field in question, because that's what we've been discussing. In the case of electric flux density, the divergence theorem states that the closed surface integral of that vector field is the same as if you took the divergence of that vector field and then integrated it over the equivalent volume. So again, and let's just write this out in words first. So what this means is that if you integrate a vector field, or in our case, a flux density, D, over a closed area. So no, it has to be closed surface area, so that would be this closed integral of d dot ds. It's the same as the first step is take the divergence, and then the second step is integrate. I said use words, so we'll use the words. It's the same as taking the divergence and then integrating over the volume. And if we think about our knowledge of Gauss's law, we can kind of show this already, right? Because in differential form, when you take the divergence of the electric flux density, what do you get? You get rho v, right? So if we plug that in to what we had before, you're simply stating you get Gauss's law in integral form, right? Closed surface integral of d gives you the volume integral of rho v dv. Right, so it's basically a substitution of Gauss's law in differential form into Gauss's law in integral form. But again, this works for all vector fields, and it comes in kind of handy. We use it in situations outside of electromagnetics, because in some situations, the closed surface integral may not be super easy to calculate. But on the other hand, the divergence and the volume integral might not be too hard to do. And so in that case, you can just take the divergence, get the charge density, and then do the volume integral, and you would end up with the same result. And in many cases, so going back to what I said before, the surface integral, you may not work out. Remember when we were describing the surface integral and using that to calculate things, you need situations of symmetry, right? So surface integral may need symmetry. And sometimes when you don't have that, that would be a very specific situation where then in that case, instead, you may want to just take the divergence and then do the volume integral. So that's just another tool that you can use in your toolbox. Every now and then, you might be solving something, or you'll read a textbook solving something, and one of the tricky pro moves is they'll just say, oh, let's use the divergence theorem and do this different kind of integral. And that's always a good way to impress people, because you're moving in between vector calculus integrals, so people get from loss to still loss, but you get to show that you were able to solve the problem this way, and everybody's really impressed, and you go home happy.